Morning, everybody. We're going to move on today to a newer section that's a little bit more arithmetic based. It's a little bit more algebra based. And so what we're going to be looking at today is what's called surds and other radicals. So you are familiar with a radical. And so a radical is any number that can just be written with the radical sign. And as a reminder to you all, this root sign or this radical sign right here, if there is nothing written, it's assumed to be a square root. If it's another type of root, it'll have another thing written for the index there. And then a surd is a more specific type of radical. This is a real irrational radical. And that word surd has a Latin/Arabic root, and it basically just stands for an irrational number. So some examples of surds are like the square root of 2, the square root of 3, the square root of 5, or the square root of 6. If you evaluate those on a calculator, they are irrational numbers. They will go on for forever. Radicals, so something that's a radical but not a surd would be like the square root of 4, because that has a for sure answer. The square root of 4 is 2, and so we would say that that is not a surd. It is just a radical. So the square root of 1/4 would be a radical, but it also would not be a surd, because if you take the square root of 1/4, square root of 1 gives you 1, square root of 4 gives you 2, it would just be 1/2. Now, as a reminder, for the square root of a here, when we're talking about radical a or the root of a, it's a non-negative number such that if you multiply those two square roots together, it's going to give you that value. And a couple of things to quantify here. So the square root of a is never negative when you're just evaluating it. When you're doing an equation, that's a different story, but when you're just evaluating, it's never negative. So as a general rule of thumb, the square root of something is going to be positive or 0, just not negative. And then a square root of a is only real if a is greater than or equal to 0. So we get into those imaginary numbers if it is not. And two other properties that we've got here. So the square root of a times b can be rewritten as a square root of a times the square root of b. So like to simplify, or to show you all what that means like the square root of 3 times the square root of 7, we could rewrite that as the square root of 21. This is just a fact of math. And similarly, we can do that with division. If we had the square root of a divided by b, we could rewrite that as the square root of a divided by the square root of b. So like if I had the square root of 25 over 16, I could rewrite that as the square root of 25 over the square root of 16, which would be 5 over 4. So just to illustrate those two properties for you all. So we'll actually go and get some practice here now. So the first thing, so we are in the red book on chapter 3. So the first thing that we're going to do is just practice using these properties up here to write these as single surds. So if we have the square root of 2 times the square root of 3, just think to yourself real quick, okay, square root of 2 times the square root of 3 is going to give me the square root of what? So that is the square root of 6. We can multiply surds freely. Now, over here, multiplication and division, they generally follow the same properties. They are inverses of each other. But so when we've got the square root of 18 divided by the square root of 6, we can multiply and divide surds freely. So we're going to rewrite that as a single radical here of 18 over 6. And we can reduce 18 divided by 6 to the root of 3 or the square root of 3. And so something to remember here, something to think about. is that when we have these radicals, for us to evaluate them, for us to get them into simplest form, what we want to do is make sure that we've picked out the largest excuse me. Sorry about that. We want to make sure we're taking out all of the largest perfect squares, and so that the number under the radical is the smallest possible sign. So what we've got to do when we're dealing with square roots is we've got to hunt for these perfect squares here. So let me rewrite this list actually. So the square root of 1 is 1, the square root of 4 is 2, square root of 9 is 3, the square root of 16 is 20 or is 4. I don't know why I was writing that. I was thinking of the next one. 25 is 5, square root of 36 is 6, and so on and so forth. Because what we want to do is that when we're rewriting these, when we're trying to write surds in simplest form, we want to say, okay, can I rewrite 72 here as any of these that I'm writing down? And kind of a way that you can check to see, can I rewrite this as multiplication? So like, obviously I can't write 72 as 81 times a perfect number. I can't do 64. 49 times 2 is 98, so that wouldn't work. So then you want to start big and then work your way down. So I'm going to say, okay, 36, can I divide 72 by 36? I can. 72 is 2 times 36. So I'm going to rewrite the square root of 72 as the square root of 36 times the square root of 2. And what that's going to let me do is I'm going to now, well, we know what the square root of 36 is. We're going to simplify that into 6 times the square root of 2. And we're going to say, well, that was equal to, this is the simplified form of the square root of 72. And all that really is to do is to help you get a better number approximation for it. The square root of 2 is approximately 1.4. So all you'd have to do to figure out what the square root of 72 is equal to is 6 times the square root of 2. And again, I do want to emphasize that that is simply multiplying the square root of 2. So if you take the square root of 2 here, and then you multiply it by 6, you get 8.48. And if you do 72 and you take the square root, you get 8.48. Those are equivalent. All we are doing is manipulating it to make it easier to work with. So we're going to be doing a lot of surd math here. So then the next thing that we're going to look at here is just doing more math with these things. So we've got 3 square roots of 5, and we're squaring that. So what we're doing here is saying, okay, well, there's actually, that means that there's 2 of these things. So we've got 3 square roots of 5 times 3 square roots of 5. And so if the order doesn't matter on multiplication. You can even put multiplication signs in between those just so that you know that. And we're going to say, okay, well, if I multiply 3 and 3, that's going to give me 9. And then if I do the square root of 5 times the square root of 5, by definition of the square root, that should give me 5. And then 9 times 5 is just going to give me 45. Just going to give me 45. So what I want you all to do real quick on example 4 right here, I want you to pause this and see if you can be the one initiating the math. This kind of combines a little bit of everything that we've talked about so far. So pause it right here real quick, see if you can get this, and then unpause it to see if you get it once you're done. So we're going to so the order here doesn't particularly matter, but I'm just going to do this multiplication first. So I'm going to say the square root of 6 times the square root of 10. That's going to give me the square root of 60 divided by the square root of 12. So then what we can say is that if these are both under square roots, we can write this as one fraction underneath a root here. If we get the square root of 60 divided by square root of 12, that's the same thing as the square root of 60 divided by 12. And we're just going to simplify that. So 60 divided by 12, that's going to be the square root of 5. And that's as small as we can make that number. That is as small as we can make that number. So now, so that's multiplying and dividing surds. Now, when we are adding and subtracting surds, which is what we're about to look at, what we need to understand is that we can only combine like surds. So we can only add things together if they are the same radical, same root, same inside. So like here, and if you read these problems out loud to yourself, you can get a little bit of intuition here. So like if I do 3 square roots of 3 plus 5 square roots of 3, think to yourself, okay, what is that going to give me? So if I do 3 square roots of 3 plus 5 square roots of 3, how many square roots of 3 am I going to have? That needs to be the thought process when we're saying that. So the answer to that is just 8 square roots of 3. Similar to adding variables. When you're adding, this part isn't changing because this is assumed. What's changing is the amount that's multiplying this surd right here. So again, these are just like adding it's the same thing as adding 3x and 5x. It would be 8x. But instead, we're using the square root of 3. So then we've got 2 square root of 2 minus 5 square roots of 2. Think to yourself, okay, what would that be? That would be the same thing as 2x minus 5x. That would be negative 3 square roots of 2. So we can add and subtract those things freely. If they are not the same, if they are not like surds, then we can't do anything with them. It just stays what it is. So, so right here on this example right here, for example 6, we've got 2 square roots of 75 minus 5 square roots of 27. And if we look right there, there is nothing there that we can do to simplify this right now. So the only thing, we can't combine these because they're not like surds. So the only thing that we could do to simplify right now would be to get this list of roots right here and see if we can rewrite these things. So let's break down these radicals just a little bit. So when I'm doing 75, let's see, 64 can't divide it, 49 can't divide it, 36 can't divide it. 25, I believe, can divide it. So 75 is, so I'm going to rewrite this as the square root of 25. So 75 is 25 times 3. And then I'm going to do the same thing for 27 here. So for 27, I'll start with 25 can't divide it, 16 can't divide it, 9 can. So I'm going to rewrite 9 as the square root of 9 times the square root of 3. And so when we're simplifying kind of we want to check to see if these radicals can break down. So let's see. Check to simplify radicals. And then we can add and subtract if necessary. So now we've got 2 times the square root of 25 times 3. I'm going to simplify that to 2 times 5 times the square root of 3. Over here, we've got 5. I'm going to simplify this square root of 9 to a 3. And then we've got times the square root of 3. So if we continue to clean this up, we've got 10 square roots of 3 minus 15 square roots of 3, which will give me negative 5 square roots of 3. Negative 5 square roots of 3, which is a lot more simple than what we had to start. You could figure out what the negative 5 square root of 3 is by hand a lot more quickly than you could the original expression right there. That's the whole point of what we just did. And so we're going to continue to work on simplifying these things. So now we're going to look at some where we expand using multiplication and addition and subtraction. So again, with these things, when you're multiplying surds, the rules are such that they operate just like variables. So if you multiply the square root of 5 times 6, that is just going to be the same thing as x times 6. It would just be 6 square root of 5. Now, when I distribute the square root of 5 times the square root of 5, that's a negative square root of 5. I'm going to get minus, if I do square root of 5 times square root of 5, those are going to cancel out. That will give me the square root of 25, which will just be 5. And I'll write that out just to prove my point there. That will be 6. So that will be 6 square root of 5 minus 5. Just to show my point there. So then we're going to look at another one where we actually have to distribute using surds here. So if you want to pause this and give it a try, you are more than welcome to. I'm going to go ahead and start distributing. So we've got 6 times 1. That will just give me 6. If I do 6 times 2, surd 3. Now here's the thing. This 6 is just, like when we write that, we're just going to write 6 times 2 square root of 3. Like the 6 isn't going to be multiplying the square root of 3 here. The 6 is only going to be multiplying the regular number. We multiply surds by surds, regular numbers by regular numbers. So then we got the square root of 3 times 1. That's just going to be the square root of 3. And then square root of 3 times 2 square root of 3. We can write that, so I'll just write that as 2 square root of 9. 2 times the square root of 9. And we'll clean that up in just a second. I could have just written that as 6, or 2 times 3. But I want to really illustrate those surd laws to you all. So we've got 6 plus, so this is going to be 12 square root of 3 plus a single square root of 3. Now 2 times, that's going to be 2 times 3 here, which I'm just going to make 6. And then we're just going to simplify this. We're going to clean up what we got here. So the 6 and the 6 can be combined. We've got 12 plus, and then if we combine these two surds right here, we got 12 square roots of 3 plus 1 square root of 3. That's going to give me 13 square roots of 3. 13 square roots of 3. So we're going to look at a couple more, and then we're going to look at division by surds, and then we will call it a day. So what we're going to look at now is still some multiplying, but we're going to look at multiplying specific types of surds. So we've got 5 minus the square root of 2, and that is squared here. So again, if you want to try this one yourself, you are more than welcome to. If you want to pause me and be like, all right, Mr. Price, I'm pretty sure I get what's going on here. Be my guest. So if we do 5 times 5 there, I'm going to get 25. 5 times the negative square root of 2 is going to be minus 5 square root of 2. Square root of 2, negative square root of 2 times 5 is going to be minus 5 square root of 2. And then negative square root of 2 times negative square root of 2 is going to be positive square root of 4, just multiplying those surds together. So then if we clean this up, that's going to be 25 minus 10 square roots of 2. The square root of 4 is just 2. So then I'll combine those to be 27 minus 10 square roots of 2. Pretty standard, pretty easy peasy there. Now, the next one right here that we are multiplying, the next thing that we are multiplying here, we're actually multiplying something here that's called radical conjugates. So what radical conjugates are they have the same first term and they have the same second term, but the sign on those terms are different. And we're going to actually look and see what happens when we multiply radical conjugates together. So if we've got 7 times 7 there, that's going to give me 49. If we do 7 times negative 2 square root of 5, that's going to give me negative 14 square root of 5. If we get 2 square roots of 5 times 7, that'll give me plus 14 square roots of 5. And if I multiply these two things together, 2 square roots of 5 times negative 2 square roots of 5, 2 times 2 is going to give me a 4, and then that's going to be square root of 25. You could have just put a regular 5 there. I like to really hammer home these rules, though. So, and what's going to happen with radical conjugates? The reason that that's significant is these middle terms right here, negative 14 square roots of 5 plus 14 square roots of 5, those actually cancel out. So what we're left with is 49 minus 4 times 5. So 49 minus 20, which is going to give us 29. And so the thing about radical conjugates is that whenever you multiply them together, your answer has no radical. And that is significant. This is going to have consequences for what we do in the next section here in just a second. It's an important property that when you multiply by the conjugate, the middle cancels here, and you end up getting the answer with no radical, because the radical gets multiplied by itself as well. So that was multiplying, adding, and subtracting surds. So the other section that we're going to look at today is going to be division by surds. Now, the issue with dividing by surds is that typically that means you're going to be dividing by a number that never ends, an irrational number, which means that the division that you're going to be doing never ends. So what we try to do is we like to get rid of those surds in the denominator. And so that can look like one of two ways. One of them is the radical conjugate that we just looked at. But if you've got a square root in the denominator, if we had something over the square root of a, what you're going to do is multiply the top and the bottom by the square root of a divided by the square root of a. And the reason we do that is that square root of a over square root of a is 1. So it's not going to change the value of the number. Multiplying something by 1 just gives it itself, but it will no longer be dividing by an irrational number. So the biggest issue here, so we're going to rewrite this with an integer denominator. Square root of 5 is a number that never ends. Dividing by a number that never ends is a no-go. So what we got to do is say, okay, well, what could I multiply square root of 5 by? If it's just a square root, you're going to multiply it top and bottom by itself to get rid of that denominator. And what that's going to give us, 6 times the square root of 5 is just 6 square roots of 5. Over square root of 5 times square root of 5 is just 5. That's called rationalizing the denominator. We just made the denominator not irrational. We rationalized it. So take a look at B real quick and think to yourself, okay, what is it that I have to do to rationalize that? The issue is this radical in the denominator. The two things in math that we do not like 0. We do not like irrational numbers. So if we multiply the top and the bottom by the square root of 7, we're going to get 35 times the square root of 7 over 7. And what we can actually do there is we can even simplify this fraction a little bit further. Now we can't simplify what's underneath a surd with a regular number. It can only be another regular number. So, but what we can do is say, okay, well 35 over 7, 35 divided by 7, that's just going to give me 5 times the square root of 7. And this is way simpler than what we were just working with over here. Way easier to calculate. Way easier. So there's whenever it's just a single radical term, it's pretty easy to solve. Now, the issue becomes when you've got something adding or you've got something subtracting there, what you have to do is multiply by the radical conjugate. We saw up here that if you multiply by radical conjugates, that the answer has no radical. So that's our surefire way to get rid of them. And so you can see if it's a plus the square root of b, we'll do the opposite, a minus the square root of b. So we can go ahead and look at this in practice to simplify some surds. So right here, if our number that we want to simplify here is 5 divided by 3 minus the square root of 2. So we are wanting to multiply this by something that will cancel out the radical in the denominator. So we've got to use the radical conjugate. We're going to multiply the top and the bottom with the same first part plus the square root of 2 here. And so what we're going to do is we're going to multiply that top and bottom, and that's not going to change it at all. 2 plus the square root of 2, or 3 plus the square root of 2, excuse me, I cannot talk. And so when we multiply here, what that's going to do, you can start top or bottom, it doesn't matter to me. Let's see. So 5 times that 3 will give me a 15. 5 times the square root of 2 will give me 5 square root of 2. And then on the bottom, we've got 3 times 3. That's going to give me 9. 3 times the square root of 2 will give me 3 square roots of 2. Negative square root of 2 times 3 will give me minus 3 square roots of 2. And you can see there that we're going to have those radicals canceling. Negative square root of 2 times positive square root of 2. That's going to give me negative square root of 4, which that will simplify. So let's finish this out. So we can see we can see here that let's see, the top is going to stay the same for right now. The bottom, those middle ones are going to cancel, and what we've got left is 9 minus the square root of 4. 9 minus, that's just a 2. So that's going to be a 7 for our denominator. And this is considered our integer denominator here. Our integer denominator. And so, I don't know, when I was making these, I don't know why I included this last problem here. But you know what? I'll do it again real quick just to round us out. So the issue with this one, this isn't a radical conjugate problem. This is just a simple, we've got a radical in the denominator, and that is our issue. So to get rid of a square root of 3, all that you have to do is multiply by the square root of 3 to the top and 2 at the bottom. And all that's going to do, that's going to give us the square root of 6 over 3 times the square root of 9, which again, the square root of 9 is 3. So this is going to give us the square root of 6 over 3 times 3, which is 9, just to kind of really send that out. So if you all have any questions on surds or radicals, if you're wondering about any of the algebra steps, or if you're just confused on a step, please let me know. Join on Zoom, shoot me an email, we can work something out. I promise you. And you all have a good rest of your day. Bye.